Today we're going to be doing polynomial regression. Woohoo! Let's hear it. Yeah. Woohoo! All right. And which means the reason I have supplement after that is because it's not actually a section in the book. So everything you have will be on the notes. And so essentially the exercises we're doing for most of the class today will be your homework. And again, I'm not physically collecting this and putting little grades in my math lab, but this is what you would be expected to be able to do, say, on some type of assessment. So I think this is kind of fun stuff. I mean, to me, this is what this course is all about, is looking at real data, because this is the type of thing when you go into the professions you're going to go into that you will be needing to analyze stuff. And if you are going to be looking at modeling, this is the type of stuff you'll be doing. Remember, there's no day classes on Monday. Some people like unaware sometimes of long weekends. Of course, I know them way ahead of time for the schedule, but we have Monday off for day classes. If you have night classes, I believe those are still on. So you have a nice long weekend, stay out of trouble. Wednesday's classes next week are Monday's classes? Yeah, it doesn't affect us, but some of you who may have like Monday, Friday classes, or Wednesday next week follows Monday's schedule. It's kind of a weird thing. They used to do this at UMass all the time. At least it's the same day of the week. At UMass, they would sometime make Tuesdays, Mondays, and it would mess everybody up. So next Wednesday, when you come back, there'll be a quiz on classes 24, which is quadratic functions, section 3.1. And then both days we did 3.2, which was Monday and Wednesday this week. So remember, I made that little reversal. If you were not here on Wednesday, I made a little change in the schedule. Today's class was supposed to be Wednesday, but I put polynomial graphs on Wednesday. So it's basically 3.1 and 3.2. You get those two sections down and those 3 homeworks down, you should be golden on Wednesday, especially with your little index cards, which many of you do not take advantage of. I don't understand, but you know, it doesn't hurt to bring in a few notes to help you remember some things. I am going to request, I put this on every single lecture note for you to do preview exercises. Maybe there's a couple people in the class that might do it. I don't really know, but I'm almost begging you, please, please. And I don't beg often. Would you please do preview exercise 110 on page 364? And I'll give you a hint. It's a long division problem. So it's just with numbers, it's just a division problem. I just want you to review that process, because when you come back on Wednesday, we're going to be doing long divisions with algebraic expressions. So it's a really good idea to just review long division as you've learned it, and then we'll show the comparison with algebraic expressions. So yeah, if you don't have a book, or somehow you haven't done any homework and you just want to know what that problem is, I can get my book for you and show it to you, okay, after class if you want. Any questions about anything coming up? Anything at all? Okay. So let's talk about polynomial regression. You don't have, this is the graph from Monday's class. I just threw it in to remind you, so you don't have this on your lecture notes, but this is where we started on Monday. So want to start us off, Nathan? Okay, so Monday we started off class with this scatter plot, and we talked about the fact that we wouldn't try to model that data with either a straight line or a parabola, which would be called quadratic regression. Parabola is called quadratic regression. So if you were looking at data like this, if you had a picture like this, say on your final exam, and you were trying to figure out what type of polynomial to fit, what degree polynomial to fit, what are you going to look for? Like, what do you look for in the data that will help you try to figure out, should I do a 3rd degree, a 4th degree, a 5th degree? What sort of things do you look for to help you? Lando? Right, what are those points called? Do you remember? The turning points, right. So remember when we talked about this on Monday, we had a story to this. We said starting in 1960, natural gas was increasing, and then it decreased for about 20 years, and then it increased again, right? We didn't use the terminology turning points then. We were just talking about what we observed. And then you all fit some type of curve to this data, and we all did a different thing, you know, and we might look like that. So yeah, that's one of the keys you look for is how many turning points are there, right? And in this particular case, there were 2 turning points. So how do we go from the number of turning points back to the smallest degree you could be? How do we go from the number of turning points to the degree, Brendan? You add 1, because remember, to get the maximum number of turning points, you do n minus 1, right? That was how we discovered the maximum number of turning points. So if we have 2 turning points, you basically just add 1 to both sides. So we know the smallest degree, this is called the minimum degree. The minimum degree that we could use to model this data, the minimum degree, is a cubic polynomial, which would have like x cubed, some number in front of x cubed, okay? So that's how you would begin when you put this data into your calculator and you go to your table, to your test to see what you'd want to calculate. So let's just do this real quick. I'll just do a little review with you. So remember, we go to stat, and we would enter this data. We'd have 5 data points to enter. And then if you wanted to try to figure out what type of regression, notice you start having your choices: linear regression, quadratic. Now we've already ruled those out. So if I had my data already in here, I would scroll down till I hit cubic regression. And then I would perform my regression just like I did with linear. Now, all of the steps, so I know that it's been a while and you might forget, I put all of the steps on how to do a regression at the end of today's lecture notes, okay? So you'll have a chance to do all of these regressions, but I wanted to give you a sense of how you look at data and how you figure out, well, should I start with a 2nd degree, a 3rd degree? Would a 4th degree be better? Okay. So let's take a look at a set and we'll do it together. So, and I forgot last night. I reminded myself when I went home. I just rewrote this first part of this lecture because I found this data online like over the weekend, and I thought it was really interesting. And it's the number of full-time women in the labor force in millions with children under the age of 6. If you go to the U.S. Bureau of Labor Statistics, they have tons of statistics for children of different ages and people in the workforce. So I thought this was interesting, and the reason I thought it was interesting, I can't prove to you because I forgot the data, but I guess you'll have to believe me. And I can bring it in on Wednesday to show you. So suppose we were looking at this, and there's no picture for you, so you really don't know yet what would be the best model for it. So what you want to do is you want to put it into your calculator, and you want to see a scatter plot. That's always the place you start. So in this particular case, I'm going to let T be the number of years since 1970. I could have picked any beginning point. I could have said, let T be the number of years since 75 if I wanted. But I just decided to pick something that would be easy to do the subtraction. So you could look at these and say 5, 10, 15, 20, 25, 30. So let's write down what our different values of T will be. T will be 5, because 1975 is 5 years from 1970, 10, 15, 20, 25, 30. So that's the values we're going to put right above each one of these. So that will be L1 list in our calculator. So this will be L1, and L2 will be right here. So when you see 4.851, that means 4.851 million women were in the full-time civilian labor force in 1975 with children under the age of 6. Okay, so let's put this into our calculator, and this will give us a little review. So you go to stat. Now remember, make sure your diagnostic is on. That's always the thing you want to check. Go down here to second catalog, and go down and make sure your diagnostic is on, or you won't be able to get your R values. Okay, so I think they're probably still on from when you did linear regression. So I'm going to make sure my diagnostic is on. I hit enter, and then you hit enter again until it says done. All right, so hit stat. We're going to go to edit. We'll hit enter, and I'm going to go now to L1, and I've got a class. Oop, I don't even have L1 and L2, do I? Okay, I'm going to have to reset it. All right, so let me clear out one of these two columns here. So I'm going to use, don't get confused, I'm going to use L3 and L4, but you can use any two columns you want, any two. So we're going to enter 5, 10, 15, 20. Kind of sounds like a game, doesn't it? 15, 20, 25, 30, and then we end at 30, which is the year 2000. So one of the things you notice so far is that the data is increasing from 1975 to 2000. We don't know whether it's sort of increasing at a steady rate, which would be a linear model, or if it's increasing quicker, which maybe would be quadratic. So that's why we got to get a picture of it. So now we put in our number of women in the workforce, 4.851, 5.886, 7.322, 8.732, 9.587, and then 9.736. Okay, so I've done that. So now it says we will find the line of best fit and the parabola of best fit. So we're going to perform a linear regression and a quadratic regression. Now, the one thing I want to just point out for you is when we were doing linear regression, we looked for the correlation coefficient, which was R. We looked for the value of R. Remember, R talks about the strength, and you remember this from your project, and the direction of a linear relationship. Okay, linear. That's all R measures. It only measures the strength and the relation in the direction of a linear relationship. We're now going to be looking at data that's not linear. So when we look for a quadratic regression, there's not going to be a little baby R sitting around. So to make comparisons when we're doing regressions now of polynomial functions, you're going to use something called R square. So every single regression you run will have an R square value. And to tell you what that means, you would have to take an introductory statistics class. Okay. If you're interested in that, I can tell you in my office hours what that means. But this R square value is something you can use as a comparison for all of your regression, and that's all you need to know. If your R square is higher for one type of regression, that means your model's a better fit than when your R square is smaller. Okay, and for all of your regressions other than your baby linear regression, they're all going to have capital R's with them, and with linear regression, it will have still small R square. Okay. So we're going to just run a linear regression and a quadratic regression, and I'll review the steps with you. So again, you go to your stat button, you go over to calc, and we want to go down and hit our linear regression 4, and we hit enter. And now we tell it what lists we have, and I believe my lists were L3 and L4, so I come here, second 3 is my L3 button, second 4 is my L4 button, and then I want to tell it what Y variable to put it in. So I go over to my vars, and I shoot over to my Y variables, I hit enter, and I want my linear regression equation to be put into Y1. So I hit enter, and then I hit enter one more time, and I get all of my information. So let's write this down. So my regression line is going to look like this. Y hat, A is the same thing as my slope, because A is taking the place of M. Now remember, with our polynomials, A would be considered the leading coefficient, right? So A is positive. We know our right arm's up and our left arm's down. All right, so A is the same thing now as our leading coefficient. So we write the whole thing in 21107 0.42857x plus what's B? 3.991866. Well, that's going to repeat when it goes 66667. So I'm just going to put that little bar above the 6. My R squared value, that's what I want to use as my comparison. Not, yeah. You are. Okay, so let's go back to my list and see if I made a mistake entering anything. Okay, and we'll compare our list. So let me just write the R squared value down. Okay, good. All right. I mean, not good, but you know. So there's R square is 95.959. Pretty nice R square value, right? Close to 1. Now remember, our R square values are going to never be, they'll never be negative like our correlation coefficient because you're squaring something. Okay, so you say, okay, well, that's not a bad model. Let me take a look at the picture and see how close it comes. Do you remember how we get the picture of the scatter plot and all that? Before we even get to zoom 9, what do we have to hit? Where do we put all of our stat plots? Do you see the word stat plot anywhere? Yeah. Right here above y equals, right? You hit second stat plot. And so we want to turn on, okay? It's time to turn on. And then you go down and you tell it where your data is. My data is in L3. Did something funny happen? It won't. Did you have like bad batteries? No, everything says yeah, you made a mistake in you got one, like you have one list with say 10 entries and another with 9 or 11, so they don't match. That's all it is. Okay, so then we hit zoom 9, and there's our data, and there's our linear regression, our line of best fit. Okay, so if you look at that data, notice we have this data from 75 to 2000. You see an increase, and then what looks like it's starting to happen with the data. It's starting to curve, isn't it? We don't have any data for 2005 and 2010. I have it, but I forgot it. Okay, so you really don't know what happens beyond 2000. What will this straight line predict for you if you go beyond the year 2000? It's going to continue to increase at a specific rate, right? What is the rate? Here's your rate right here, 0.2 million women per year. That's what it's telling you will start to happen. 0.2 million, 0.2 of a million, 200,000 women a year will be continually being added to the non-civilian labor force after the year 2000. Okay, so we don't know. So this is where, remember, the word extrapolation, that word is used when you try to make a prediction beyond your data set, beyond your data range. So if you were trying to predict the number of women in the workforce after 2000 or before 1975, because you have two ends to this data set. If you go outside your data set, that's called extrapolation. If I wanted to try to figure out how many women I had, say, in 1983, right? 1983 is within my data set, okay? So that's called interpolation. Now, I've been using these terms, but I don't think we've ever like written them down. Interpolation is like within your data set. Beyond data range, yeah. Within data range, and that's when I use the word estimates. I mean, I'm just a little picky about this, but I don't care whether you use estimates or predictions. I usually save the word predictions when I'm going outside. All right, so this looks pretty good. What about trying to fit a parabola? What kind of parabola? What would be the leading coefficient on this parabola? Do you think the parabola would be a happy parabola or sad if it was going to try to fit this data? Sad, because you expect that the parabola would increase and then sort of try to hit these 2 points and then start to come down, right? So you should expect that your quadratic should have a negative value for A when you throw throw in your quadratic regression. Okay, so let's do our quadratic regression now. You hit stat. You've already got your data in there, so you don't have to do that. You hit calc, enter. Oh, I hit one variable stats. I don't want one variable stats. I want quadratic regression. There we go. So I'm going to have to clear this and do it again so we don't get mixed up. Okay, so you go down to 5. That's quadratic. Okay. Is your calculator working now, Julia? Okay, I'll fix it. Okay. And now what do we want to do? Tell it where the data is, L3, L4 for me, maybe L1, L2 for you, or wherever you have your data stored. And then now I want the regression, the equation for the quadratic regression. I don't want to put it in Y1. I want to keep Y1 there. So I hit vars, yvars, and I'm going to tell it now to go to Y2. Okay, and let's hit enter and see what we get. So here's our quadratic, ax squared plus bx plus c. Notice our leading coefficient, a, is negative, and these are the values for b. So I write down my quadratic equation. X squared, and then my b value, x, and then my c value. What's my r squared value here? 0.985, right? Which one has a better fit, the linear regression or the quadratic regression? Quadratic. So I would choose the quadratic regression for my model. Okay. Sometimes students will say to me, but what if they're really close? What should I do? If you get r squared values that are fairly close together, you want to choose your simplest model. So in other words, if I had an r squared value for my linear regression that was like 0.982 or 0.978, and it's really close to this, I want to go with my simpler model because then all my calculations are much easier to do. So if they're close, go with your simplest model, your model with the smallest degree. Okay? That's just sort of the rule of thumb. Whoever's doing the research, who's ever out there doing the research on particular data, will have a better feel for what the data is doing. And so they then may use some other criteria rather than going with the simplest. But for us, we go with the simplest. Let's take a look at this plot. Second stat plot. Well, we're already turned on. And let's see what happens. Zoom 9. There's our linear regression. And there's our quadratic regression, and that goes through really nicely. So look, this quadratic hasn't yet reached its peak yet, has it? It's going to continue to increase a little bit here, not quite as rapidly as the line. And then it's going to predict that the number of women in the civilian labor force will decrease. So I actually looked at the data, I think it went through 2011, this particular data set. And this data reaches around 10 million, a little more than 10 million, and I'm trying to remember the year now because I did look at this last weekend. It was like around 2005 or 6, I believe. And then guess what? It starts to decrease. So I'm always interested sort of sociologically or historically what starts to happen that causes some of these changes in data. When you have data that's increasing over 30, 40 years, and then suddenly it starts decreasing, what's happened to cause that? So that's a little bit outside the scope of this class, but those are sort of the things I think about. Was there something that happened or has happened? Was that when the economy started to, say, get poorer? So there were women that couldn't go out and work, so they tended to be home versus it being a choice. I don't know like what sort of all the factors are here. But again, the people that tend to work with this type of data set or make these observations would have a better sense of that. Sometimes it's a historical reason. You know why. One of my students a couple of years ago was a veteran, and he, for his project on linear regression, Orlando, could we not do this, please? Thank you. I know you're helping him, but he was a veteran, and for his linear regression project, he put the number of U.S. troops and Afghanistan and Iran. And it was following a nice linear pattern. And then all of a sudden, one year it jumped up. And if you, I don't know how old some of you were during the Bush-Cheney years, but there was a year where we did what was called the surge, where they sent in like a huge influx of troops. And that was shown in the data. And clearly my student knew what had happened then. And we talked about that in class, that that's what the data showed, was that time in history where we had this incredible surge in the Iraqi war. Okay, so that's pretty much it for today. And we have, let's just see how we would do a prediction again. I think it was why did I pick the year 2011? You better put that away, Julia, please. What you just took out of your pocket. Okay, so the year 2011, right? Well, I picked this because I meant to bring the data set. This was the year that we started to see a drop, or it was either the peak or the drop. So let's see what each of these models would predict for 2011. These are the types of questions I've been asking you all along. So how would I find the answer to this if I've got both of my models in here? What would I do with the year 2011? How would I figure out what its value of X is? Logan? X31, that's what where does he get the 31 from? Remember, we're saying X is the number of years since 1970. So 2011, take away 1970 is 31. Now, 41, okay, 41. Okay, so your calculator does all this work for you. You've got your two equations right here, folks, Y1 and Y2. So set your table, second table set. You don't want to start at 1. You're interested in finding out what's happening to this, the number of women in the civilian labor force in the year 2011. So depending on how curious you are, since our data stopped at 30, you might want to start at 30. You might want to start at 35. I'm kind of curious. I'm going to start at 35. I'm going to go up by 1 year. This is 0.1 year. I'm not interested in that increment, so I'm just going to change that to 1. Then you go to your table, and you can compare each particular model and what they predict. Notice your straight line's going up much quicker than your parabola. Your parabola is slowly increasing here. Your parabola actually fits the real data much better than your linear. Okay, so we're going to go out to 41. And notice at 41, your linear model predicts that there will be 12.646 million women in the U.S. labor force, the civilian labor force. So that little sign for Venus is a symbol used for women, in case you didn't know. And then the Y2 is 10.3, looks like 3 repeated, so I'm just going to put 10.3 million women in the U.S. civilian labor force. And without knowing much about the data, it's kind of hard, but I would feel fairly confident with my quadratic. I don't know if I'd feel as confident because it's really increasing at a pretty steady rate here, and I don't know if that happened or not. I might feel confident about both of them without much knowledge, but because unfortunately I've seen the data, I know that the quadratic's much closer. So let's go back and just try a little bit of using our knowledge from Mondays and Wednesdays classes. Using the leading coefficient test, let's determine the end behavior of each model. Which model do you think will be most accurate in modeling the future number of women in the civilian labor force? Well, the leading coefficient for our linear model was positive, right? So A was positive, which means it's going to increase, right, without bound. As the years go on, as we move to positive infinity, Y is also going to move to infinity. With our quadratic, our leading coefficient A sub 2, which is the first value that we looked at, the first value in our quadratic regression, is negative, which means as the years move on, eventually at some point we're going to have model breakdown because it's going to predict that the number of women is negative. Okay, so at some point, but that could be far out, long before any of us are alive with this model. Eventually we'll have model breakdown. So the future here is relative. If it's the near future, I would say the quadratic regression would be a better model for the near future. Okay, beyond that, I'm not going to I wouldn't use either one of these models. I'd probably have to gather new data and then maybe try to find a more appropriate model. Okay, so you don't ever want to go too far out into the future with these models. You got to be cautious. Okay, so you've got a bunch of data that available to you, and you have, let's see, 20, 40 minutes to work through these in class. And you have your flags. I'll help you out at any point with any questions you may have. And Julia, I'll try to get your calculator fixed for you. So right here, I didn't write it out, but this should say without bound. Without bound. I said it, but I didn't write it. And this down here, Jonah, with the quadratic, because y is going to negative infinity down here, you would say it decreases without bound. Yep, right. And if you look at the first coefficient in that model, the first coefficient is negative. Right here, see, negative. So that's going to decrease without bound as x gets bigger and bigger.